Okay. 2 minutes, yeah. So why do we care about volcanoes? Lots of reasons. As you've heard about from Sam's talk in particular yesterday, they're probably the major forcing for the past millennium. And they're, more generally speaking, a really great test case for climate models. So, typically after an eruption, the stratospheric aerosol loading maxes out about a year after the eruption, and then there's an e-folding time of about a year, so it takes maybe, a few years to get back to normal. But of course, that's kind of size dependent. And typically, again, for a typical eruption, we see maximum effects in the year that follows the eruption, and then things relax back to normal. And that was particularly the case for the Pinatubo eruption, where in this article by Sarden et al., they viewed it as a natural experiment with which to probe the physics of a handful of climate models in that case, or 3 realizations of the same model, and they were able to show that the model was getting the right answer for the right reasons, with the water vapor feedback really kicking in, and drying of the troposphere going on as there was cooling. So I think there's a long tradition at this point of using volcanoes to probe climate model physics, or more generally our understanding of the dynamics of the climate system. And so let's try and do the same in LMR. There's also some renewed interest in volcanoes, particularly because of the hydroclimate impacts. And again, that's one thing that we can probe with LMR that we couldn't probe with previous reconstructions. Here is a figure from Trenberth and Dye from 2007, where they looked at only one eruption, that was Pinatubo again, and they were able to show that the globally average stream flow decreased by a fairly significant amount. Of course, it's a little hard to tell statistical significance from one event. So it would be nice if we had a bit larger sample. Isles and Hegel also try and do something like this over the instrumental period. But again, they were limited in the length of the records that they had available. So I think for most of the continental regions that they looked at, there was an average of maybe 3 to 5 eruptions that they could look at. So of course, that's not really enough to do statistics. So we would want to have a much longer sample. Let's say, why not 2,000 years instead of 50? So we could do this. So again, why do we expect drying over land? Same reason why there was a drying of the troposphere. You cool the troposphere by Clausius-Clapeyron. The relative humidity or absolute humidity must go down, and then there's a slowdown of the hydrological cycle overall, and in particular over land. And of course, this would have strong implications for agriculture, and so it's important to understand why in future considerations or in future situations we may be faced with that. In particular, because of the potential for geoengineering to be implemented if we do nothing about our greenhouse emissions, which looks increasingly likely. And as preposterous as solar radiation management schemes sound, unfortunately, especially with the politicians we currently have, it seems like people might be tempted to actually do that. And so it's really important to understand natural analogs to geoengineering, which volcanoes definitely are. So in fact, that was one of the points that Kevin Trenberth has been making, is that you would expect very serious hydrological consequences for solar radiation management strategies. So again, volcanoes are a good test case for looking at what happens then. And then there's some more esoteric reasons for looking at that. This is a painting from Carl von Marr from 19th century depicting one of the strangest societal movements of the Middle Ages in Europe. And it was, it's recounted here in this quite the colorful prose of Richard Stothers in this article, where he was talking mainly about the so-called Samalas eruption that at that point was dated around 1258 or 1259. Now we know it's 1257. But be that as it may, those years were particularly bad in Europe for all kinds of things: crop damage, famine, and it led people to believe that there was some kind of godly punishment, and the obvious solution was to walk from town to town and flagellating themselves with the success that we know. So there are definitely also some societal impacts of climate, and this is one reason why there's this newly formed PAGES working group, VIX, the Volcanic Impacts on Climate and Society, because definitely there's a lot of historical precedent for looking at the volcanic impacts on society. And I think LMR really provides a really wonderful crucible for looking at all these things, or tying them together. So a little bit more about geoengineering. This is the results from a recent paper by Rike et al. And essentially, they try to look at what kind of aerosol optical depth you need to stabilize climate in the face of various emission scenarios. And I just want to give you an order of magnitude here that depending on the emission scenario or what time horizon you're looking at, it's on the order of maybe 0.05 to 0.2. Which, you know, they're dimensionless units. So keep that in mind, because we'll look at eruption or aerosol optical depth due to volcanoes that are in that range, if not much bigger than that. So just keep that number in mind. All right. So what do we know about volcanic forcing over the past millennium or the Common Era? You heard from Sam yesterday that that's a very significant source of uncertainty. In data model comparisons, is that we don't even know the forcing that well. But that, I think, changed quite a bit. Of course, we're never done, but there's some recent paper by Michael Seigel that's done some really amazing work collating a bunch of ice core evidence from both poles and really increasing those data sets by an order of magnitude. And they've been able to do some amazing things, like revise tree ring chronologies. If you know a tree ring, if you know dendroclimatologists, you know that they don't easily take to criticisms to their chronologies. So if you can convince them an ice core chronology is more precise than a tree ring chronology, that's quite an achievement. But so the timing of certain eruptions has been moved. Like, for example, the Kauai eruption that was previously dated at 1458 is now dated to 1453. And these things don't seem to matter to you a whole lot, except that if you are going to do year-by-year comparisons, it's pretty damn important to know what year things happened. Also, the size of the eruptions in terms of the sulfate aerosol loading is now better constrained with more measurements. So that's not to say it's not going to change in the future, but I would argue that this is a very major improvement, the likes of which we probably haven't seen in a decade or two in our knowledge of volcanic forcing. Now, for all of the things we know, which for most eruptions, we know the locations, and we certainly know how much polar deposition of sulfates there were, and that's how we reconstruct really the size of the aerosol plume. There's also a lot of things that we don't know. For example, the exact time of the eruption. Again, as Sam's work has shown, it can be absolutely critical what month the eruption happens. And unless there's some documentary evidence attesting to that, we usually don't know. And that's why, as she said, in the Gao et al. Data set, that by default every eruption happens in April, which most likely wasn't the case. And yet it's very consequential. So keep that in mind for the other comparisons. Whenever you see a question mark in the rest of my slides, it means we don't know where the eruption happened or when it was exactly. We also, of course, don't know the atmospheric circulation at the time of the eruption, and yet that's often probably the biggest predictor of what the aerosol veil ends up looking like, rather than just the location of the eruption. So it depends on both, but there are situations where the stratospheric winds are such that they can spread a northern hemisphere volcanic aerosols into the southern hemisphere or vice versa. So we don't know that, we probably never will. All we know is what ended up falling over the poles. All right, so recently, this is work by Matt Toohey, mostly also with Michael Seigel. They produced this new data set called the Evolve 2K, which is what I'll be using a lot in my comparisons. And one of the things it does, like some previous ones, it basically reconstructs things in bands of latitude over time, actually at monthly resolution. So it does give you some idea for those eruptions where we knew the timing. You actually know it down to the month. And also you have some general idea of how it's spread in latitude, and that the hope is that this will be a significant improvement for the PMIP4 modeling cycle that will actually give the model something a little bit more precise. So I'll be using that in the rest. And yeah, once again, you're looking at, this is the size of kind of the geoengineering aerosol optical depth that we're looking at, and that corresponds roughly to the Krakatoa eruption. Right? So you're talking about, in order to stabilize climate in the late 21st century, you'd need to have essentially a Krakatoa eruption every year. That's the scale that we're talking about. All right, I promised you some LMR. Here's some LMR. So this is, by the way, most of these simulations were done by Michael Erb when he was still at USC, and this is a figure he made. that very nicely illustrates the timing of cooling that you can observe in northern hemisphere or southern hemisphere temperature, and how it coincides with volcanoes. So he's highlighted here as these triangles, the 40 largest events, again in that Seigel et al. 2015 data set. And you don't need a PhD in statistics to see that there's a really good correspondence between a lot of these temperature minima and the timing of eruptions. It's not a perfect correspondence. Now there's some games you can play. You notice immediately that the northern hemisphere temperature, which is in red here, is much more variable than southern hemisphere temperature. We've talked about it before. It's generally the case during the instrumental era as well, and that's because we think either it's a complete lack of coverage over the southern hemisphere, which is definitely a possibility, but also there's more ocean, there's a bigger heat capacity in the southern hemisphere. So one thing I was interested in is maybe the interhemispheric temperature gradient increases when there's certain kinds of volcanic eruptions. And I did not really find evidence of that in LMR. I did not find anything significant. But it's very clear that for most of these eruptions, and again, I think it's location dependent, they end up having a much stronger eruption in the northern hemisphere, even when they're tropical. So one cool comparison that was done recently by our colleague Kevin and Chukaitis, and I mentioned some of these results yesterday, the N-Trend Consortium, which is an international consortium of mostly dendroclimatologists who've put together these mostly northern tree line series, I think overall 54 tree ring chronologies, and that they've used to produce a spatial reconstruction of temperature since 750 CE. And one thing you see here is a superposed epoch analysis in both this Pages 2K based LMR reconstruction and the N-Trend reconstruction. So superposed epoch analysis, I think probably most of you are familiar with it. It's just compositing things where you define by convention 0 being the year of the eruption. You remove the mean of the 3 years prior to the eruption to kind of even out whatever low frequency variability is going on. And then you look at what happens in subsequent years. So in LMR, we see a very strong cooling over Western North America, over much of the Arctic and Northern Europe. And you can probably see it here, but there's a very, very mild warming here over Alaska. And I wouldn't point it out other than the fact that we also see very similar features in this N-Trend reconstruction. So we very clearly see warming here. It's, of course, quite a bit noisier. They're not using a smooth climate model to interpolate things in space, so you'd expect it to be noisier. Also, there are some grid boxes in there that are not covered by any observations, and with that particular statistical framework, that means that the variance goes down to 0. So you would expect to see differences, but I think Greg can attest that we were pretty shocked when we saw that figure the first time, that the agreement seemed to be as good as it is, both in terms of magnitude and spatial pattern, including there are places that seem to warm mildly, like Western Alaska, and they warm both and both. Now, it's a weak signal. It's probably just a fluke, and our eyes tend to be attracted to flukes, unfortunately, but that's certainly very encouraging. And I also showed yesterday some of the temporal non-hemisphere behavior that's also very convergent between the two. So it's immensely encouraging that using data sets that have some overlap but are very different for the most part, the methods that could not be more different, we find volcanic impacts that are so convergent between those two approaches. Now, one thing that we can use that for is to test GCMs, and that's exactly what has been done actually for quite some time. So this was a picture from the IPCC AR5 from the paleoclimate chapter, and one of the things that was pointed out, I forget exactly which figure that was, but they did a superposed epoch analysis, very similar flavor than what we did, and in red you have the CMIP5 models of CMIP5, PMIP3, and in gray you had an ensemble of northern hemisphere temperature reconstructions that was used there. And there's two things that you notice here, is that overall the cooling is much more pronounced in the GCMs. So I think for northern hemisphere temperature it's around maybe 0.3 degrees, and for the reconstructions it's closer to maybe minus 0.15 or 0.2 degrees Celsius. And it also tends to happen a little bit later in the reconstructions, and persist for longer. So there's, of course, a fairly wide envelope, but it's generally true that the recovery, so the volcanic cooling appears to be more intense in GCMs and to recover more quickly than in the reconstructions. Does this hold true as well in these newer products like LMR and N-trend? Definitely yes. I mean, in this case, we're not looking at the models, but definitely we see that there's a fairly extensive recovery that sometimes it takes up to 15 years to get back to normal. So the relaxation time in that case can be, on the order of a decade. And one question, of course, and that's the case both also in N-trend, although it's a little bit clearer in the N-trend composite than it is for the spatial reconstruction. And one question is, well, is this a physical feature? Is this a real feature, or is this an artifact of the data that we are using, that we are putting into the soup? And one reason why we suspect that, I'll get to that later. So you can do the same types of things, superposed epoch analysis. This is what I did just in LMR, just to showcase the kind of multivariate investigations that you can do. So the color contours are surface air temperature, and the black contours correspond to 500 millibar geopotential height. And you definitely see a close correspondence in most cases between the height field and the temperature field. That's not completely surprising, because the only thing you have to constrain geopotential height are surface proxies, which probably, their response to geopotential height is probably mediated through surface climate anyway. But you see that usually the strongest response happens over Northern Europe, that it could be on the order of maybe 2 degrees locally, even though, if you look at the global mean, you only get maybe, the Northern Hemisphere mean, you get maybe 0.2 degrees average. So there are strong regional disparities in this thing, and I'm not going to interpret too much, the various wave patterns that you see over time. I tried to elaborate a very clever uncertainty quantification for this, and it was so clever that I couldn't find any results. So to be determined, to be continued. So I'm not showing you the significance results here, other than to show that you definitely see things changing slowly from year to year. Now, one question is, how much of that is dependent on eruption to eruption? Yeah, Jean, quick question. Mm-hmm. Yeah, all of this is annual. Now, yeah, going back to this, I should say, N-trend specifically targets May, June, July, August temperatures, because that's the season where trees grow in the Northern Hemisphere. And we nominally this is nominally a reconstruction of annual temperature, and it's because we had an annual PSM, but I think we'll see probably some interesting differences when we redo this with the latest LMR with seasonal bivariate, or at least the seasonal PSMs, where we should be seeing even a closer correspondence between these things. So stay tuned for that. Okay, why I wanted to go somewhere else with this. Oh yeah, things got a little. Okay, well, let me continue with this. So what other impacts are happening in LMR? So you can look also at the hydroclimate impacts, and they're clearest. So in that case, this is precip in the year of the eruption, and then this is the average over the next 5 years, which in most cases doesn't appear to be very significant. And probably a better way to do this would be to look at the year-by-year evolution. But still, it's fairly striking that in the year of the eruption, you see a very clear signal in tropical precipitation, with a drying over the maritime continent, more intense precipitation along the equator in the Pacific. So something like a Walker type, like a weaker Walker circulation. So something that would be consistent with an El Nino-like signal. Did I gloss over that one? Oh yeah, sorry, it comes later. So if you want to look at the temperature field, the El Nino signal in there is not very clear. I mean, there's a very weak warming in the Eastern Equatorial Pacific that does not appear to be significant, owing to, in that case, I think, a permutation test. Much of the impacts are over Northern Europe or Western North America. So while qualitatively similar, we still have to dynamically resolve this conundrum that there's a very clear, very big signal in precipitation, but it does not appear to be a very strong signal in temperature. I'm not sure I have an explanation for that. One thing that is interesting and that I want to explore some more, there's some very interesting numerical experiments done by Chris Colos a few years ago, or just last year, where he looked at the impact or the location of volcanic eruptions on the hydroclimate impact of that. And essentially the ITCZ moves to the energetically deficient hemisphere, or it moves away from the energetically deficient hemisphere, which means that when you have a northern hemisphere eruption, the ITCZ moves south. When you have a southern hemisphere eruption, the ITCZ moves north. And when you have tropical eruptions, things get a little interesting. So that's definitely something that I need to look at more in LMR, and we definitely have the means to do that. So let me move on and actually do some of this. To finish that temperature story, there is a lot of evidence. There's a very extensive literature for an El Nino-like response to volcanic eruptions, of which I've been guilty of contributing as well. It does appear, for a long time, the GCM people, so they told us, no way, it doesn't appear. It doesn't happen. And then now that CESM is doing it, now it's in favor again. So at least, and Sam showed this as well, depending on where the eruption is, you see usually an El Nino-like warming in the winter following the eruption. It does not appear when it's a southern southern hemisphere eruption. So that points again to the necessity to discriminate between tropical northern hemisphere and southern hemisphere eruptions. So let's do a little bit of that in the couple of minutes that we have left. So I did make these figures last night. And definitely, a lot of it is just staring at pretty colors. But there are some interesting things here. So this is, again, from the Evolve2K dataset. This is the aerosol optical depth. So here, what I did is, there's the year of the eruption, which in that case would be 1108. So that one, I don't believe, was exactly located, although all we know is that it's a so-called bipolar eruption. It's not a psychological diagnosis. It just means it was found at both poles. And so most likely it's tropical. So because the exact latitude was unknown, I think it was set on the equator. And so what you see here is the evolution of the aerosol optical depth along latitude, going from -90 to +90. And here you have just the integrated, the global integral of that. So, not a particularly fearsome eruption. But you can see some interesting features here where there appear to be some wave trains happening in geopotential height that also have a surface expression in temperature. In some cases, you see some very clear hydroclimate impacts, like this one, for example, looks a lot like what I was showing you with drying of the maritime continent, more intense precipitation along the equator, and that one would have a weak El Nino-like warming, and also some wave trains that look very much like they could emanate from the central tropical Pacific. You can do that for a bunch of these. The point here, without assaulting you with 100 pictures, is that there are some definitely still open mysteries. 1258, 1257, the Samalas eruption, is definitely the strongest of the Common Era, probably the third largest in the Holocene. So this was a big eruption. The aerosol optical depth is believed to have exceeded 0.45. So you're talking about pretty significant solar dimming. It was a tropical eruption, happened right here in Indonesia. And in that particular reconstruction, it's believed to have relatively symmetric impacts. And yet, the climate impacts are not all that impressive, at least if you believe LMR, right? You have cooling in the regions where you'd expect it based on the composite. You also have some of these interesting wave trains, but it's not very big. On the other hand, you go to much smaller eruptions. So we have a bunch of these. So Kauai is a big one, and that one really lights up. That one seems to have very big surface expression and also these stationary wave patterns. But that one was about 50% smaller. If we believe, again, the ice cores. And most remarkably, the 1601 eruption, that was about half as small as the last one, but that one seems to have had massive impacts over at least northern hemisphere temperature. And you see peak cooling on the order of 5 degrees in some places in the very high Arctic. And also, obviously, very intense disruptions of northern latitude circulation. So it's still unexplained why the largest eruptions might have a relatively muted temperature impact, and some much more modest eruptions seem to have had a very strong impact. Perhaps there's some just projection of internal variability there. So there's a lot more to harvest from that. Yeah, and that one, one reason why it shows up so strongly in LMR is that the trees really suffered from that. So if you use the trees to reconstruct volcanic forcing, the trees would tell you that this was the largest eruption of the past millennium. That is to say, you should never trust a tree to tell you what the forcing was. But anyway, so I'll skip on that. So let's move on to a couple of things. So to me, the most interesting thing, which is a feature that Greg had uncovered actually right at the beginning of LMR, as soon as he had the first results in hand, and those results, by the way, have survived several LMR versions, so we're relatively confident that they're not an artifact of the algorithm, although they might be an artifact of the data, is that there is this roughly 15 Kelvin drop. That number might change a bit again as we move the PSMs, but the extended recovery is something that's been here for a long time and still seem to be there. So is this a physical feature or is this a reconstruction artifact? And one reason why we believe it might be the latter, so if you trust that it's a real feature, there is some support in the literature, this paper by Pausata et al. For some big eruptions to have an effect on the AMOC, essentially induce a large anomaly in ocean heat content that then gets propagated through the ocean circulation, moves the ITCZ in the Atlantic, and in turn that has an effect on ENSO, on the ENSO growth cycle. So it ends up having teleconnections throughout the tropics, with ostensibly in that case more of a Northern Atlantic mechanism. So there is some support, and these are model simulations using, I think, the Norwegian Earth System model for decadal-like or decadal scale features after big eruptions. So it's not like it would be completely physically impossible to imagine that big eruptions would trigger these anomalies and that they could persist for a while. On the other hand, there's a lot of debate in the literature about how trees feel about volcanoes. Mike Mann had a paper a few years ago arguing that they were muting the response to volcanoes because they essentially shut down when it gets too cold. Martin Tigley had a retort to that the year after or so, or 2 years after, showing actually they could show in at least the instrumental record that just the opposite happened. That because trees are sensitive to both climate and light, and because of the decrease in photosynthetically active radiation that happens during an eruption, they sort of feel a double whammy effect. So their growth gets interrupted, and they tend to, if you interpret this solely as temperature, you might tend to overestimate the actual cooling. So this appears to be more of a problem for ring width than for density. So that's yet another reason for doing more density records. I'm looking at you. He works on tree ring density records. But there's a lot more experiments that we need to do within LMR to try and disentangle these things, of whether this extended volcanic recovery is an artifact of using ring width or modeling them inappropriately. Again, this was using a linear annual temperature PSM for the trees, and clearly we know that that's not optimal. So to be continued. Next time you hear this talk, things might be different using the latest version of LMR. So to conclude, volcanoes are really important natural experiments, and so the LMR is a really great data set to try and see what happens during volcanic eruptions. We see temperature estimates, temperature coolings that are globally in line with previous reconstructions, but we have sometimes like a very, very weak support for that El Nino hypothesis. At least it's not completely disagreeing with it. The lead feature is the long recovery and whether it's real or not, and so what are the dynamics. Oh, I didn't finish this one. There's also very clear response in terms of geopotential height, whether we trust it, whether how well LMR verifies for geopotential height is less clear. And there's also very clear changes in tropical rainfall, in particular the location of the ITCZ. which is something that I feel we can constrain from independent measurements. So that's definitely something we're going to look into. But also remember that eruptions are like snowflakes, without making a bad play on words. And there's a necessity to look at them individually, because the composites won't tell you everything. So that's what I'll be spending my time until IGU. And then, of course, there's a lot of open questions. We'd like to see what the other fields look like that we haven't really looked at before. I'm particularly curious about what happens in 018 once we have incorporate the ICESM as a prior. And there's also some really nice questions about how it can constrain GCM physics, in particular the implementation of volcanic aerosol forcing in PMIP models. I believe that LMR is actually going to give us a handle on that, which would be very exciting, because it would actually be one of the few, if it works, one of the few examples where paleo observations actually feed back into the model development cycle. So stay tuned for that. And sorry for going over time.
Yeah, great talk, Julien. Thinking back to a couple of the figures in my talk, I've been thinking about the idea that going back in time with less of a proxy influence on the reconstructions and the variance in the ensemble mean